Okay, so I'm going to talk about optical microscopy in turbid tissues, basically tissue imaging with microscopic methods and with an emphasis on nonlinear optical microscopy. This actually is a nice image of kidney tissue, and it's taken with coherent anti-Stokes Raman scattering. This is the kind of the idea of what we want. We want these kind of snapshots of tissue, high resolution, okay, so sub-micrometer resolution, and some form of contrast that is meaningful. Hopefully, contrast that tells us something about the presence of certain molecules at certain locations. The sub-micrometer resolution is kind of important. It allows us to see individual cells and sometimes even details in cells. So subcellular resolution can be extremely useful for diagnostic purposes. So if you're a biomedical person and let's say you're a histopathologist, then you used to look at slides of cells with the same kind of resolution, so sub-micrometer resolution, looking at the ratio between nuclei and cytoplasm and so forth. So that kind of resolution is very useful in the biomedical sciences, and the microscope, the optical microscope, can give you that resolution. Okay, so that's the whole idea. High resolution snapshots of tissues. Okay, so microscopy, what is a microscope? We all know what it is, I don't have to tell you that. But just to kind of like reset the button on this, that is the most important element of your microscope. Okay, that's right. So that is an objective lens. It does all the magic, okay? Because it basically allows you to take light in, illuminate a certain area, and then image that light, in this particular case, with a combination with an extra lens right here onto an image plane right there. You put a camera there and you can see the image that's taken, that's sitting right here. Okay, so and this lens can really give you an interesting magnification and high resolution. Those are two different things, by the way. You have a magnification, which is how many times you amplify the image, and you have a resolution, which is like resolvable features. This lens does both of them, so it can actually magnify the area you're looking at. That's one. But number two is it can actually resolve features with high definition. Okay, so this is a kind of a regular way of doing it. You send light in, and you just literally take an image from here, project it onto a camera, and then you get images like this. There's a little cell here, and the resolution is what you're kind of used to, or familiar with, from an optical microscope. It's a sub-micron. This is another way of doing the same thing, really, but instead of using a light source, an arbitrary light source, that's for instance a light bulb, you use a laser. And the laser has a very interesting property. It is collimated light. And if you send collimated light into a perfect lens, you create a focal spot. Let's have a look. There it is. This is a focal spot. It's a tightly focused spot, and the size of this focal spot should correspond to the resolution of your microscope. And so the width here is about 0.3 microns or so, and the length here, the depth of this focus, is on the order of a micron. So that's what these high numerical aperture lenses do. They create these beautiful focal spots. They either operate in this condition, which is a wide field imaging operation mode, or in this focused mode, but the resolution is the same between the two. The resolution is just defined by this lens. Okay? In this focus mode, you can actually do some very interesting features, and that's what we'll be focusing on today. The light is generated only from this location here, in the focal spot, is then captured by this lens and projected through this lens onto a detector. This detector is not an imaging detector. It doesn't create an image, it just collects the number of photons that were emitted from this focal spot. Okay? So if you want to take an image in this case, you have to move the focal spot to the next location. So you have to scan, raster scan across the sample. And that's the idea of focused image. Laser-based imaging is called laser scanned imaging. And you build up an image. So that will take a little while. However, you probably know that you can do that very fast. You can have very fast scanners. You can take an image like this in less than a second, which is about the same time it takes to take an image like here. So these two things are kind of complementary. Okay? Different approaches will give you approximately the same result. However, this method has some advantages, as you will see in 2 seconds, in particular for tissue imaging. Okay? Because if you have a well-defined focus, you can play some tricks to reduce effects like scattering in tissues. that is very hard to get rid of in this mode of operation. Okay, so let's have a look at these focal fields. These are absolutely crucial in laser-based microscopy. Tiny focal spot, let's have a look very close. You probably have seen this graph, and you will see it once again. The speaker after me will actually tell you in detail how this thing comes about, this focal spot comes about. There's an amplitude, and there's also a phase. Now, for most intents and purposes, we don't really care about the phase too much. And in the first half of the talk, I will just completely ignore this aspect. But as you will see in the second part of this presentation, the phase actually becomes important. This is the electric field distribution in the focal area. This is the phase of the electric field. Okay? And so I'll explain a little bit more about that in about 30 minutes or so. Again, the width of this amplitude distribution in this dimension, in the lateral dimension, is about 0.3 microns, 300 nanometers. And if you draw a line from here to here, that is the axial dimension. It's about 1 micron, full width half max. So that is really a tight little area, tight volume, from which you can generate signals and then capture those signals with a photodetector. Okay, so let's have a look at this. Hopefully you can see this. Again, you can see here the kind of the focal field, but below and above there's also excitation light. So this is what we call an excitation cone. The light comes from below, it travels up, it is condensed or confined here, and then it kind of diverges again out. All right? Now what you should know is if I take a plane through, let's say the focal plane, and I just, at each location, I just look at how much intensity there is, and integrate in this plane that's given over here, I find a total intensity of S. Okay? So it's a total intensity, light intensity, that travels through this plane. Now, if I take another plane, here, a little lower, you see this thing is wavering out, but of course, if I do the same trick, I find the same total intensity. The total intensity is just spread out over a larger area. Okay, so I would take even lower plane here, then, once again, the total amount of intensity that travels through this plane is still S. Okay? It is not as condensed as it is over here in space, but clearly the light that travels through this plane between here and here is exactly the same. Why do I say that? Because this is kind of the basis of the following statement. There's no depth dependence in the total intensity if you do regular light microscopy. If you focus this light into this cone, then at every plane the photons will go through. So that means if you have a signal generating mechanism, for instance like fluorescence or absorption, every plane contributes to your optical effect that you're trying to measure. Okay? You're not exclusively sensitive to what happens here, really. You measure everything that happens in this cone. Okay? The signal from each plane contributes equally to the image. The out of focus light cannot be ignored. It plays a role. Okay? So in focus microscopy, we tend to focus only on what happens in this area here, because that's where the signal apparently is the most bright. However, every plane contributes as well. And so this is going to be important. We have to deal with this, and this is especially important in tissues, because the tissue occupies this entire space. It is big, it's not thin, it's thick. Light encounters material everywhere along its path, below the focal plane and above the focal plane. There can be optical interactions that they can contribute to your signal. So here's an example. Blurry images, that's what you get. This is a cross-section through a piece of tissue, and lots of cells, as you can see. They're labeled with fluorophores. This is fluorescence microscopy. This is one plane, one slice out of the whole tissue. You get a very crisp image because the planes above and below this plane do not contribute. However, if you don't do that, if you don't exclude those contributions, you see something like this. You get very blurry images. You get light from everywhere, okay, from the planes above and from the planes below the focus. Now, in focus, the light rays that originate from focus will still be focused mostly onto your detector. So they will recreate an image, and that's why you see structure in this image. Okay, so there's still structure in the image, but at the same time, there's also a lot of defocus contributions that are overlaid. And so this is not good, and this is a typical thing you would encounter if you just put a slab of tissue in your microscope, your regular microscope, you will see things like this. And it's very hard, and this is not the way to do tissue microscopy. Okay? You have to solve this problem. There's two basic ways in which you can circumvent this problem. Two basic ways. The first one is, you probably have heard of it, confocal detection. What it does is really, it attacks the problem from the detection side of things. Okay? So you focus your light, as usual, you have a laser beam, you focus it to a tightly focused spot in your tissue, there it is, and then light comes out, it's emitted, and then it's going to your detector. Now on the detector side, you make sure that the only thing you detect must come from this area, from this volume. And that you can do that with a confocal pinhole. You probably know that. If you put a confocal pinhole in front of your detector and you align your system well, you're only sensitive to photons that come from this volume. If it comes from here, comes from there, it has different type of divergence, and then it doesn't actually peep through the pinhole. It's not imaged back onto your detector plane. So, in effect, what we do is, on the detection side, we reject the contributions from elsewhere. We only detect the contributions from here. So effectively, you're sensitive only to what happens in this area, and that means the plane below and above it has become invisible. That's great. That's the principle of confocal detection, addressing the problem on the detection side of things. You can also address the problem on the excitation side. How does that work? Well, that's what happens in nonlinear excitation. What happens is, instead of having light emerging from the planes above and below, it is not generated in the first place, because due to a nonlinearity, only light within this focal volume is able to generate the signal. Below and above, the intensity is too low, and the efficiency of nonlinear signal generation is not enough to generate an appreciable signal. So, on the excitation side of things, you attack the problem from the very start, so to speak. You don't generate the rogue photons in the first place. Okay? So, the solution is confinement. You can find either on the detection side, or you can find on the excitation side. So, and that works beautifully well. I mean, both methods work great. So here's a beautiful picture that I just ripped off the internet. Here's the coordinates if you're interested. This is a Drosophila brain slice that labeled a lot of the bodies, the bodies of the neurons, here with a fluorescence indicator. And this is a three-dimensional reconstruction of that big part of the brain. You see, you can actually create beautiful three-dimensional reconstructions of tissue. Another example, two-photon microscopy. This is again, a brain tissue slice. This is the depth, and these are labeled neurons once again. The bodies are here, the axons, they go deep into the tissue here, and you can actually go very deep with this kind of modality. So what happens here, we have a probing volume that is small in all dimensions, in 3 dimensions. We scan it literally through the tissue in a 3D raster kind of format. And that works both in confocal as well as in the nonlinear excitation mode. Okay, so, but we will focus here on what happens in the tissue. Okay, so far we haven't really factored in the effect of the tissue itself. Even if you have no tissue, or the tissue doesn't scatter whatsoever, you still have to work a little bit hard to get rid of out-of-focus light. But now the tissue itself will also introduce some problems, as you probably are well aware of. Okay, so what is going on? If we want to create a beautiful focus inside a tissue, we will encounter several problems. Okay, so this is my schematic of a tissue. There's some structures in there that scatter. Okay, we're not going into great detail because there's people here in the audience that can explain that much better to you than I do. But this is my focus that I'm trying to create. I'm setting this light cone into my tissue, and evidently, it's not going to be a beautiful, unperturbed focus. Okay, on their way, those photons will be scattered, and consequently, the focus that I create will be distorted. So there will be distortion and attenuation of the excitation light. So I'm bringing in my photon beam, and already on the excitation side, I'm starting to distort things. So this focal volume here that I want to create, that should have certain dimensions, is actually going to be distorted. And as a consequence, the signal that I'm generating is going to be different than in the unperturbed case. Okay? So the signal generation is now generated in an aberrated focal volume. The focal volume is attenuated, and its shape is going to be distorted, and that means that I'm generating less photons that come from a larger area in space. That's a very different condition than in a non-scattering tissue. Okay, so on the level of the excitation light, I'm starting to mix things up. I'm affecting my situation. That has a consequence for how much signal you generate. And then finally, the signal that is generated has to propagate out of the tissue. Okay? So the photons that come, the photons will only be generated here, let's say. They have to propagate out of the tissue, but they will encounter also the scattering objects, and therefore will be, at some point, not ballistic anymore. Okay? So the propagation of the signal out of the tissue is also of interest here. So I put here 1, 2, 3 because I tend to think of this process in those steps. There is an effect on the excitation side. I'm affecting my excitation. Okay, the focal volume doesn't look good anymore, attenuated and distorted in space. The signal, therefore, is different, so the signal generation is affected. And then the signal that is being generated has to propagate out. That's the third issue that I have to deal with. Right? I want to minimize all of these things in principle. Now let's have a look at what happens in confocal microscopy. So what I'm trying to do is I'll look at these 1, 2, 3, these 3 stages of scattering in tissues for focused beams in a confocal microscope and in a nonlinear microscope, and look at the differences between them. Okay, so here we are. Number 1, in confocal microscopy, typically it's operated in the fluorescence mode. What you have to do is you have to excite the fluorophores in your tissue, and they want to be excited in the visible range of the spectrum. In order to do that, you have to put in light that is typically on the blue end of the visible. So that's why it's called a blue. Blue light has a short wavelength, as you probably know. And short wavelengths scatter more than longer wavelengths, like red. Okay, so I made this blue to indicate that this is a beam that is very sensitive, very susceptible to scattering objects. Therefore, there will be a high distortion and attenuation of the excitation beam. Okay? Because of the short wavelength excitation. That's not really good. So number 1 is already pretty bad. Then I want to generate my signal here from the focal volume, but because there's a lot of distortion, and this excitation line is very sensitive to the scattering objects, this will actually look more like that. It's a much larger area, it's attenuated, and therefore there's a much larger focal volume, and emission occurs from a much larger area. Okay? It's attenuated and it's stretched in space. That's different. Now in a confocal microscope, what you do, by definition, is, like I just said, you confine the volume that you probe. Okay? So you still probe a small volume. The confocal detection sees only the same diffraction limited focus, the undistorted focus, so to speak, and it is sensitive to only the ballistic photons. Okay? So the photons that come from this diffraction limited volume, which is smaller than actually the real volume, and then what you intercept are those photons that come back on their way without being scattered, without changing their path. Okay? Those are the ballistic photons, photons that have not scattered. So the whole confocal system is sensitive to ballistic photons on the excitation side and ballistic photons on the emission side. And as a consequence, you are missing out on a lot of photons. Okay? So confocal microscopy, therefore, is really, really sensitive to scattering. Scattering tissues really reduce the signal tremendously. And so, therefore, actually, confocal microscopy is not used a lot for deep tissue imaging. So this will indicate these photons, the non-ballistic photons, the photons that have scattered, will not be detected. And just that's a loss of information right there. Now, in nonlinear optical microscopy, things are similar but a little different, and different enough so that the nonlinear microscopy modality becomes a preferred option over confocal microscopy for tissue imaging. So what is the situation? It's right here. Instead of using shorter wavelengths, we use longer wavelengths typically in nonlinear optical microscopy. and I'll say something about that in a few moments, longer wavelengths, in this case indicated by the red color, means less sensitive to tissue scattering in general, and therefore lower distortion and attenuation of the excitation light. So I'm reducing on the excitation end of things, I'm reducing already the effect of scattering. Then, of course, I'm creating my focal volume in which I generate my light, but I just said it's distorted. That is true. That's the same effect as in confocal microscopy. You do have a distorted focal volume, so you actually generate photons over a larger area, a larger volume, than you would have had in the unscattered case. These photons then, they come from this area, from this larger volume, they go in all directions, they scatter as before. That's very similar to confocal microscopy, but the important thing is that we don't use a confocal pinhole. We have an open aperture. We try to intercept as many photons as possible. We don't need a confocal pinhole because we don't confine on the detection side, only on the excitation side in nonlinear optical microscopy. That means that you can actually see those photons. The non-ballistic photons can be intercepted if they fall within your cone angle of detection. Okay? So as long as they can be intercepted by your detection system, they can be registered as valid events, valid counts on your detector. So you have much less attenuation, both on the excitation side as well as on the detection side. Okay? So that's why I'm trying to make a case here that if you are serious about tissue imaging, scattering media, and you want to cover a certain range, you want to kind of like image in a certain volume, depth is a very important parameter, then you probably want to use nonlinear optical microscopy. And so here's a kind of a quick table that compares the nonlinear optical microscopy, and I will say much more about it in a few seconds, to linear microscopy, which is what we typically think of as linear confocal fluorescence microscopy. What is the differences? Well, first of all, very attractive. In nonlinear optical microscopy, we can actually generate molecular contrast of a lot of endogenous molecules. Molecules native to the tissue. We don't have to, we can still use labeling tricks, but we can actually generate much more contrast from endogenous molecules than we can do in linear microscopy. So molecular contrast in linear microscopy comes through fluorescence in almost all cases. And that means you have to label. That labeling is less of an issue in nonlinear optical microscopy. The penetration depth, like I kind of was alluding to, is higher in nonlinear optical microscopy because the scattering and attenuation is less because we use longer wavelengths. We use shorter wavelengths in linear microscopy, therefore this is not so attractive if you want to go deep into the tissue. There's an intrinsic 3D resolution. That's because there's confinement on the excitation side, which is not there in linear microscopy. There's only 3D if you use a confocal detector. But as we know, confocal detectors reject a lot of light if you have scattering media. There's a wide aperture detection. We just talked about it. That means you actually can detect many photons. The non-ballistic photons can be detected, at least the ones that travel backward and fall into the NA of your detection system. But in the linear microscopy case, if you use a confocal detector, you reject almost all of them. And you only intercept the ballistic photons, which is very little in highly scattering tissues. Photodamaging occurs only in... This is an interesting statement. Think about this. Photodamaging results from photoexcited processes. Okay? So let's say I'm exciting a molecule, heat gets extracted from the light field, it goes into the material. I can actually generate so much heat that I'm starting to damage the material. So, but the good thing is, the excitations happen only in the focal area. And outside, the outer focus planes do not really allow the photoexcitation to take place. So that means also no photodamaging. Photodamaging is happening through the entire excitation cone in linear microscopy. Because basically, the intensity of light, if you integrate an entire plane, is the same everywhere. That means everywhere, each plane, there will be optical excitations. And that means throughout the entire cone, you can have photo damage. So all these things are advantages of nonlinear optical microscopy as applied to tissue imaging. Okay? Now, there's some disadvantages too. So this is the advantages of analog microscopy, nonlinear optical microscopy. These are the disadvantages. Yes, photodamaging only occurs in focus, but if it happens, it can be pretty bad. The photodamaging in focus can be significant. Okay? And here, actually, you have a relatively low photodamaging in focus. So this is a balance. If you have a full excitation cone, then you can have photodamaging throughout the entire cone, but at each plane, the photodamaging is relatively little. Here, the photodamaging is nothing above and below, but in the focus, it can be actually kind of high. Okay, so this is the kind of the balance that you have. Of course, analog microscopy, this word is much more difficult than this word, which means you have to pay a price. Money. It's more expensive. And the linear microscope is much, much less expensive. Okay, so that is actually an important consideration. Oh, something happens. Okay, we're back. I thought we were back.
Maybe we can pause for questions.
Yeah, that's a good idea.
Good.
Feel free to interrupt. Yes?
I have a question. I'm just a little bit confused on like the nomenclature, I guess. So is the only difference between non-linear microscopy and linear microscopy is that you're exciting with red light and that you're opening your aperture for you're taking photons?
So far, that's what all I've talked about. Yes, those are the two ingredients I've talked about, and you see nonlinear optical microscopy. The next few minutes will be I'm telling you a little bit more about the basics of nonlinear optical microscopy, what it is and how it works. But yeah, the main differences between confocal microscopy and nonlinear optical excitation microscopy is the wavelength and the way in which you detect those photons.
Eric, can you comment a little bit about signal to noise and imaging depth in this comparison between these
Yeah.
two methods? I think that would be helpful.
Yeah.
I think there are some logical extensions from the points you've already made.
Yeah.
But
Yeah, there is actually, I'll say, there's one slide where I'm trying to say something about signal to noise as a function of depth in two-photon fluorescent microscopy. And there's a couple of effects that actually work against you. I'm not exactly sure what kind of answer you're looking for.
well, we can wait till later if the context
Right.
later in your talk makes it more sense to
Right.
address it after you introduce a few more things.
Yeah. Let me do that.
Yeah.
Hopefully, it will be less confusing.
Anyone else?
How much more expensive is it?
Well, you can probably build a linear microscope with a, even if you want to do it in a fancy way with a single mode CW laser and a regular microscope and a CCD camera, you'll be probably done for $30,000. Everything, okay? And if you want to build a similar microscope in the nonlinear optical modality, then you have to basically cough up about 10 times as much money. So it's 300,000. And actually 300,000 is very little. So it's more like $500,000. Right, so it's significant. It's a factor of 10 at least. Yeah, very pricey. So there has to be a clear advantage of this microscope. Otherwise, it makes no sense.
Where does that cost come from primarily? Are there specific factors in
Yeah.
particular that you can identify?
The cost is almost exclusively in the laser. Yeah, you can purchase beautiful CW lasers for as cheap as $1,000. But the cheapest pulse laser source that you need for nonlinear optical microscopy is about 50,000. Okay, so that's a cheap one, and you can tune. You can tune the wavelength or anything. So you don't want that one. You want the one that unfortunately costs $200,000. So that's the trade-off. Yes.
So what will be the envelope of your of the laser light you are using? I saw that there's a left spot there's a central spot and a couple of lobes,
Uh-huh.
side lobes.
Uh-huh.
So I'm just curious.
What, say again, what is your, I missed the beginning of your question.
I mean, what will be the envelope of the just
The envelope?
Yeah.
You mean the profile, the way, well, I mean, you know, that graph is kind of an indication, that's an amplitude distribution.
But generally, you just use Gaussian data.
No, this is not, I mean, the image you saw of the amplitude is actually a diffraction limited volume that is a non-Gaussian beam in that particular case. It's just basically a flat top that's coupled into a lens, and then you calculated the diffraction limited volume. So it's slightly different from a Gaussian. The Gaussian wouldn't have those side lobes.
Yes.
Yeah, that's right. So a Gauss is easy because it's an analytical solution, but it's not really exactly what happens in focus. It's not really Gaussian because we typically over-illuminate the back aperture of our lens, and that means we come in with a virtual flat field, a uniform field at the lens, and that means if you do that, if you take the Fourier transform of the flat field, you actually get side lobes.
Yeah.
So that's a non-Gaussian situation. Yeah. And if you want to really say something significant about these fields, the Gaussian analytical approximation won't really cut it. I think the next speaker will maybe say something more intelligent about that. Who knows? Okay, so very quick. I said already a lot of things about NLO microscopy, but let me just really briefly give you a sense of what it is. Most of you probably are familiar with it, so I won't bore you with it for too long. But the basic idea is that this is the main ingredient, that the signal that we measure, S, depends non-linearly on the intensity it goes in. Okay? So this N is the nonlinearity coefficient, should be larger than 1. Right? So, for instance, when it's 2, then your signal scales to the second order with the incoming intensity of the excitation light. Or, this is another version, you can have a signal that depends on 2 incoming beams, I1 and I2. It depends on both. That is also a nonlinear process. Okay, so if you have something nonlinear, then again, and we said this already, this is the excitation cone in linear microscopy. Signal comes from every contribution here. Every plane contributes to the signal. In nonlinear optical microscopy, the signal only comes from this area because there the intensity is the highest. And if you square the distribution, all those locations here, where each location has less intensity than the focal plane, will be reduced significantly due to the squaring operation in nonlinear optical microscopy. And this is an image you probably have seen many times, and I'm almost embarrassed to show you. But you see here this excitation cone. In linear microscopy, you get signal from the entire cone, and in nonlinear optical microscopy, that's from this side here, only this little tiny spot. So after and before the focal plane, you get nothing. Nothing really contributes. There's no optical communication with the material. There's no excitation taking place, only right there. That's where the excitation is taking place. That's where the signal comes from. That's where the photodamaging takes place as well. Okay, now, NLO microscopy is a family of techniques. Okay? And I'll just highlight a few of them, but there's really a lot. The most famous one is two-photon excited fluorescence. And we'll see a little bit about that in 2 seconds. But there's also second harmonic generation, or imaging of collagen. And then there's coherent Raman techniques like CARS, coherent anti-Stokes Raman scattering, stimulated Raman scattering. And you have techniques that are related to second harmonic generation, some frequency generation. And then you have entirely different approaches, such as pump probe microscopy. All these techniques, the similarity between all these techniques is really that they all depend non-linearly on the incoming excitation light. Okay, you see all these arrows here. All these arrows indicate field interactions between the material and the light. And you see it's non-linear. It depends on multiple arrows. Okay, so we'll just talk about 3 of them. Talk about second harmonic generation, two-photon excitation, and these 2 guys, coherent Raman techniques. Okay, so this is nonlinear optics 101. Okay, just to give you a feel. I think it's kind of cool to know where these signals come from. So here's a molecule. And we know those molecules respond to light. Why? Well, the light has an electric field component, and it can actually shake around electrons in this molecule. This molecule has nuclei, and it has, of course, electron clouds around it. These electrons are very mobile, and the electric field that comes in can shake these electrons around. Okay? So what the light does is just changing the position of the electrons in this molecule. This is most relevant to those electrons that are in the outer shells, or the so-called valence electrons in the molecule. They will be shaken by the incoming electric field. Okay, now how far can you shake those electrons out? Well, not too far, because they're bound by the nuclei. Okay, so if you take a coordinate, which is the distance from the electron from its equilibrium position that it was in before the field entered, then the electric field can just push them out a little bit, but at some point there's a restoring force because there is a potential. These electrons are bound, and in the first order approximation, by a harmonic potential to the nuclei. Okay, so the farther you want to pull out those electrons, the harder you have to work. That's what this potential says. Okay? Now, if you pull it out, what you do is you change the position of the electron. It's now somewhere else. And that means you actually create a polarization in this molecule. Because you have a charge here, negative, that means you create a positive charge here. So you create a polarization situation. How large is this polarization, indicated by this P? Well, that's a linear function. It's a function of distance. Okay? So this potential here, if you do the calculation, I'm not going into detail, if you pull this out linearly, then you actually create a linear polarization that grows linearly with the distance you're able to pull the electrons away from their equilibrium position. So, here's my driving field. I'm putting my field in, that's my electric field. Forget about the magnetic field, it doesn't do anything in this case. So this is a sinusoidal modulation. Electric field goes like this. What happens? The electron is going to shake like this, right? And if it shakes along this coordinate, you see the polarization is going to go like this. So let's look at in this axis here. You see the polarization comes out like that. So I'm shaking the electron along this coordinate. It's changing its position. And as a consequence, the polarization goes like up, down, because I'm shaking the electron like this. Okay? So interestingly, if I come in with this perfect sinusoidal modulation, one particular frequency out of the electromagnetic spectrum, you see that the polarization follows that beautifully. Exactly the same waveform that you put in comes out. Why? Because there's a linear dependence between the two. Okay? It's a linear dependence between the distance and the polarization. Okay, and this is exactly what happens in all forms of linear optical effects. Now, the situation is a little different if you start driving those electrons harder. Okay, so if your fields are stronger. Why? Well, because this harmonic potential is really just an approximation. Electrons are not bound by a perfect harmonic potential to the nuclei. In fact, it looks very different. And the farther you push them out, or pull them out, you see that you actually get this distortion. That is because if you pull them out far enough, you actually ionize the molecule. Okay? So this is kind of like this famous potential, the binding potential of an electron to a nucleus. It has this kind of like Morse type of potential shape. All right? Now this is not relevant here because this happens only at such high energies that you don't have to worry about it if your field that you put in is very weak. You only deal with the lowest part here. In the lowest part, everything is still linear. Still behaves like this. But if you're able to pull it out farther, which means your field you put in is higher, then you start sensing this area here, which is not harmonic anymore. In fact, if you do the calculation, you convert the shift this potential to this graph here, you see it looks like that. It deviates from the linear. Again, that only happens for strong fields, not for fields here. Okay? For fields here, it still looks very linear, but the farther you push them out, you start sensing this area here and the kind of curvature here, and you see actually this nonlinear dependence between the equilibrium position of the electrons and the polarization that you create. So now, what happens is, if I now start coming in with a field and I drive these things out very well, on one side the electron goes farther out than I expect, on the other side less far, and consequently the polarization looks a little different. It still looks sinusoidal. But if you look at the shape here and the shape here, it's a little different. In fact, On this side, it doesn't extend as much. On the lower side, it extends even more. This is a kind of a distorted waveform. So, perfect sinusoid comes in, distorted waveform comes out. And that means, if you believe in Fourier analysis, and you should, then this is not a pure sinusoid anymore. It still has a very strong sinusoidal contribution, okay, at the same frequency that you put it in, but it has other components as well. For instance, there's an overtone here, and there's something else, and so forth. Okay, so you can decompose this wave into waves of different frequencies. The biggest component is still your linear fundamental frequency, but there's other frequencies as well. And so these frequencies will be generated. Okay? Your molecule will generate those frequencies, and they can be detected as radiation. And so you can now decompose the polarization into the linear term and other terms that occur at higher frequencies, or lower frequencies if you take combinations of two different frequencies. Now, of course, all these terms that come after this linear term are the nonlinear terms. Nonlinear terms only happen if you drive the molecule hard, right? If you don't drive it hard, you don't see them. They're too weak. But if you drive them harder, then you start seeing those things. So you can understand that it only works if you use pulsed laser fields, because those have the intensities needed momentarily to actually generate these effects. If you use CW fields, then overall the field intensity is not high enough, and typically what you see is only this first term. So we need pulsed lasers with high field intensities momentarily to generate and see those forms of radiation at different frequencies. Okay, now let's focus only on this guy here for the moment. The second order contribution. This is a wave that has twice the frequency of the incoming driving field. And this polarization component, interestingly, is only there if the material has a certain symmetry. Okay, and that is the basis for second harmonic generation. And this is kind of the quantum mechanical picture of it. This is not the classical picture, this is pure quantum mechanics, but this is fun to have both pictures in mind. In quantum mechanics, the way we think about it, okay, two photons come in, one photon come out. Okay, and if you add these two energies up, then you have found the energy of the emitted field from the molecule. That's second harmonic generation. Who knows what this dotted line means? Say again? No. This dotted line means it's not an eigenstate of the molecule. This is called a virtual state. These thick lines means this is an eigenstate of the molecule. Real states of the molecule, states the molecule can actually be in. This is a state in which the molecule doesn't like to be. It's called a virtual state. And so if we go up with this, you can't park energy there. It falls directly down. This is an instantaneous process. I cannot park energy here because there's no eigenstate. The molecule can't hold on to that energy, so to speak. It will release it, typically in the form of these two photons coming out, but sometimes you get the combination of these two photons in energy. And that's a second harmonic wave. Okay? So, let's now look at what is taking place. I have 800 nanometers light in, for instance. What is the color of light coming out? Is it 1600 or 400? Yes, it's 400, right? So twice the energy means half the wavelength. Okay, there's an inverse relationship between energy and wavelength. Okay, so but look, this is interesting. 800 nanometer is pretty far to the red of my visible spectrum. In fact, it's almost outside of the visible spectrum. Okay, so 800 nanometers can be called near infrared radiation. That light is much less sensitive to scattering than is this light. Okay, so in second harmonic generation, the excitation light is less sensitive to scattering than the light that comes out. Right? If you deal with one photon excitation processes, you deal typically with wavelengths in this range, which is very sensitive to scattering. But here on the excitation side, you deal with this light, which is not so sensitive to scattering.
So
Yeah.
just going back to that picture, so just putting this picture together to what you just told us, obviously at low intensities, you put in that light, you're just going to get those two photons out. It's only when you drive it hard enough that you get this conversion.
Yes,
So this-
that's right. Yeah. Yeah, these two photons, that's right. If you don't drive the system hard enough, you will never see this photon coming out. Only when you drive it hard, these two photons can actually combine to generate this third photon at a different wavelength. And that is a quantum field explanation of the classical effect that I just explained to you in terms of decomposition of waves. Okay, so, but I did say that there's something special about this second order effect. There's a symmetry constraint on the material. Not all materials do this. And it has to do with how these molecules are distributed in space. If they are completely symmetrically or isotropically distributed, they will cancel out each other's contribution. Only when there's a non-centrosymmetric arrangement, you retain the overall effect of the second order effect. Now, there's only a few materials in biology that do this. Very interesting. And collagen type 1 is a major player in this game. Collagen has a very unique structure. It is actually non-centrosymmetric on a wavelength scale. Okay, so you see here there's a second harmonic picture of collagen. This is a molecule, but you see these molecules are aligned beautifully in these strands, and you can see that beautifully. Now, this is collagen. The signal comes from type 1 collagen. I have not added any label to this molecule. This is the molecule itself that generates this signal. So this is label-free imaging of collagen. Very useful. Very useful. What else? Microtubules have also a non-centrosymmetric arrangement. The microtubule monomers are arranged in this kind of like chiral structure here. So there's a very strong chiral contribution that is non-centrosymmetric. And so you can see microtubules in second harmonic generation microscopy in cells. Another example is meiosin. Here it is. You see the structure in your muscles. And these meiosin strands, these strands here, in the bundle are also non-centrosymmetrically arranged. And you can generate these beautiful second harmonic patterns of the meiosin in sacromers in your muscle tissue. Yes?
So, given that it's a non-centrosymmetric material, does your efficiency of generation of second harmonic signal depend on the relative orientation of the molecule relative to one?
Absolutely. Yeah.
Can you comment on that?
This is a very detailed story, but the short of it is the following. There are, okay, so people in second harmonic generation don't really know where the signal comes from. Okay? Which part of the molecule is the main generator of the second harmonic signal? They don't really know. But we do know much more about some frequency generation, which basically means I can address certain parts of this strand. And we do know there's several parts in this molecule that is, first of all, highly polarizable, and second of all, is distributed non-centrosymmetrically on a wavelength scale. And for instance, these structures here are proline residues of the biopolymer. The proline residues have several modes, vibrational modes, and they are completely in an achiral way, completely non-centrosymmetric. And so these guys will contribute to a nonlinearity that is projected on this long axis. Okay? So there's an achiral asymmetry projected on this long axis. In any other direction, it cancels out, because this is a triple helix, which is isotropic has rotational symmetry. So only on this axis you retain a non-centrosymmetry. And that's why these lines here, as you can see, really corresponds to the long axis of the molecule. Now, if you rotate a molecule like this, and you keep the light like that, you shake the electrons in this way, you won't see any signal. You have to move the molecule like that to drive it along the long axis. So yes, if I would rotate either the sample or my polarization of light, the contrast here would change.
So the propagation of light has to be along the long axis of
The polarization of light.
Polarization.
Propagation doesn't matter, but the electrons have to be shaken in this direction. If you shake them in this direction, they will not retain the second order nonlinearity.
Is there a reason you focus on type 1 collagen?
Because it's the strongest contributor, and this, there's other forms, collagen type 2 and 4, that also have this property. The other collagens seem to be much less efficient.
You know what that is?
People don't exactly know why. I mean, It probably has to do with the fact that on a microscopic level they still do, but on a higher hierarchical form there's cancellation. That means there's like randomization on a higher level. These molecules are, I mean, they're sub-nanometers, right? So you can stack them up in many different ways to make larger structures on a wavelength scale, which is a couple hundred nanometers. And so if there's too much randomization on that level, the second harmonic signal will disappear. So you need to retain the level of order up to several hundred nanometers. Only in those cases you retain the signal, and that happens in collagen 1, 2, and 4. Okay, two-photon excitation. Who has never heard of it? Everybody. Very good. So then I don't have to explain to you what this means. Okay? 2 photons in, a little bit of structural relaxation, heat relaxation here, and then you see emission of a photon. That's your fluorescence photon. This is an interesting graph because people say, okay, you just excite the molecule and it fluoresces. However, you do excite at different level as in 1 photon fluorescence. Okay, so please take note of that. You see a comparison. Okay, here, this line, I believe this is NADH, if I'm not mistaken, is a 1 photon excitation. Okay? And this is the spectrum. So if you put in light through 1 photon excitation of this color, of this wavelength, you see the absorption is right here. It's magenta line. But if I put in 2 photons with twice the energy, I'm exciting a different level. See, I got this shape. This is the absorption of the 2 photon process, which is actually a different level. So I'm exciting different levels in a molecule, but after relaxation, it falls down to the lowest singlet allowed transition here between this excited state and the ground state. So the emission is typically identical to the 1 photon emission. The excitation can be different. Here's a graph of different kind of naturally occurring chromophores that also emit and can be 2 photon excited. And you see in this range between 700 and 1 micron is a very good range to excite a lot of these naturally occurring chromophores in tissue. I don't have the labels, but there's NADH in there, riboflavins, elastin. Those are typical examples of molecules in tissues that contribute to a strong 2 photon fluorescence. An example is elastin. It is a protein, structural protein, indicated here in green. Beautiful fluorescence. So a structural protein, essential in tissue and connective tissue. It fluoresces and can be excited very well through a 2 photon fluorescence process. NADH, our favorite metabolite, also fluoresces, mainly because of this contribution here. This molecule here absorbs and fluoresces. And NADH, of course, is in every cell and is an indication of the cell's metabolism. Here you see keratinocytes, live keratinocytes that have a lot of NADH, and you see that is taking place, or it sits in the cytoplasm throughout the cell. The dark nuclei here indicates that NADH is not in the nucleus, okay? Which is kind of nice because you can count the cells. You can see the nuclei and you can see the cytoplasm. The NADH only occurs in the cytoplasm, so you get beautiful definition of those cells. That is actually an image from a live patient, the skin of a live patient. Melanin, interestingly, that's the molecule that gives you your beautiful color, is a molecule that absorbs a lot but doesn't fluoresce a lot. Okay, that's good, because if it would, we would all be glowing all the time. We do not. And that means if you excite melanin with 1 photon, you really don't see much fluorescence. However, interestingly, if you excite melanin with 2 photons, you do see actually a significant fluorescence coming up. Okay, so that indicates again we actually excite a different level in melanin than with 1 photon. And so it actually is able to fluoresce now. This is a fluorescence from melanin. These are 2 melanocytes, and they fluoresce. And we can actually record the lifetime of melanin, fluorescence lifetime of melanin, and discriminate based on the lifetime 2 forms of melanin, eumelanin and pheomelanin. They have different lifetimes. And so we can say something about the distribution of these 2 types of melanin. Very relevant. I won't go into detail, but this is one of the things you could do with 2 photon fluorescence. Here's a beautiful picture that's taken by one of our colleagues in the Beck Malaysian Institute, Mehela Balu. And this is a cross-section. This is depth, and this is lateral dimension. This is skin of a patient. Okay? And you see here the top layer, that's called the stratum corneum. Everything that's green is called the epidermis. It's basically NADH fluorescence from cells. You see here, this structure here, those are cells that are very bright. Those are cells that are just born here on the basal layer. And they actually morph into keratinocytes. And they lose the fluorescence because actually they dry out and they form the hornified layer here that forms the stratum corneum. Okay, so you see the individual cells beautifully through NADH fluorescence in a live person. Okay, below you see collagen. That's second harmonic generation of collagen. You see beautiful structure in there. You see also even deeper some fluorescence from elastin. So you see collagen, elastin, and NADH allows for a full view of the structure of the tissue. Okay, without any labels. I don't put anything on this patient. Patient just puts his hand like this, or his arm like this, and we can go through, up to this depth. So a beautiful contrast. This is very significant. You could actually do diagnostics with this without scooping out the tissue. And this is really where multiphoton microscopy can probably make a difference. Okay? It really has the potential of an optical histology. Basically looking at the tissue, come to a diagnostic without scooping out the tissue. Okay? This is the main prime potential of nonlinear optics in the clinic. It hasn't been fully realized. The potential is there. There's just a lot of other cultural barriers. Yes?
I'm just curious how you would combine these two modalities in one instrument.
Very good question. We have one laser excitation. Excitation is about, I believe, 770 in this case, 770 nanometers. It excites the NADH, it fluoresces, but the fluorescence at a certain wavelength range. The main peak of the fluorescence is around 530 nanometers. Second harmonic is generated at the same time, with the same laser beam. But second harmonic is half the wavelength, so it's 770 in half. That's below 400 nanometers. Okay, so what I can do now, I can just put a filter, one that captures the light below 400 nanometers, which is second harmonic generation, and then a bandpass filter that only captures 530. And so I can separate the two emissions from the tissue onto separate detectors. And detectors can just operate in parallel, and you can capture those two signals at the same time. Yes?
You said melanin has two-photon fluorescence.
Yeah.
Do you have any kind of feel for what different level of pigmentation does that impact the two-photon fluorescence in a patient, say, with type 1 skin versus type 5 skin?
Yeah, so that story is basically to discriminate eumelanin from phenolanin. They have different lifetimes. It's actually slightly different, but just different enough so you can discriminate them. Those lifetimes are relatively independent of the quantity of those chromophores. So, if I have a little bit of eumelanin, it still has the same lifetime than if I have a lot of it. Now, the color of your skin depends just on the concentration. Okay, the darker you are, the more eumelanin you have. The redder you are, the more phenolanin you have. Right? So, but they retain their emission properties, independent of how many neighbors they have. Okay, now here's the same picture once again. Let's look at this a little bit more carefully. If you look at this picture, and again, the depth here is about 120 micron. Okay, so keep that number in mind. It's very kind of relevant. So beyond 100 microns, things get a little murky. Because look at this structure here. I see a lot of definition here. I see just like more, hazy things from here. It doesn't mean your tissue is hazy there. It means you just get, less meaningful signals back. So up here, as we know, the focus is still relatively confined, not so much affected by scattering because it just went into the tissue. It's compressed, the resolution is high, the signal to noise is high, because you don't get a lot of signal from the other contributions outside of focus. So high resolution, high signal to noise. If we go deeper, hopefully you can see that, now move it in here, what happens? Focal volume is more extended due to scattering. It's also less bright, okay? That's because I've lost a lot of photons. The non-ballistic photons don't arrive here, and so the overall intensity of the excitation light is much less. So there's enlargement, and there's loss of excitation light here, and this is at the level of excitation, and the light even has to come out still. Okay? So one way which people try to avoid, kind of counteract this, is by simply cranking up the excitation light when you go deeper. What does that do? It doesn't change the scattering properties of the medium at all. But what it does do, it, on average, delivers more ballistic photons to this area. You just crank up the power, the number of photons, on average, more photons will arrive here. Okay? That means you can still generate pretty good signals from those regions deep. So you would say, that's good. I mean, I can just keep cranking up and go deeper and deeper. However, it doesn't work so well. Okay? First of all, you do have a larger volume, so you get less resolution there. You get a little bit contribution from the outside region as well, because these areas actually start to come and they actually generate more and more two-photon fluorescence as well. But the main killer here is this. You have to bring this light all the way into there. Up here, where the illumination cone is wide, okay, so you normally don't generate a lot of light. But if you crank up the power here, especially at the interface where nothing has been scattered yet, you actually have a very high photon flux. And what happens is, at these regions here, you actually start generating light out of focus. Okay? Just because you have to crank up the power so much, you have enough photons to induce two-photon fluorescence even for the unfocused beam. So you get contributions a lot from this area that adds up to the photons here, and it seems as if you have a lot of green here, but actually part of the green comes from the area here. All right? Has nothing to do with here, and it's there all the time. Wherever you go with this beam, there will always be surface, and so you get an overall haze that kind of overlays your image. And your signal to noise is going to be very bad. Yes?
So also the other thing, I don't know if this is important or not, but you said that the second harmonic generation you're using 770, and so your second harmonic generation is below 400.
Yeah.
And that, I imagine, can be absorbed a fair bit as it
Yeah.
travels back. Is that also?
Yes, of course, yeah. And there's also, on the way out, there's also attenuating factors that don't work in your favor.
But it differentially hampers the second harmonic signal relative to the fluorescence.
Yes, that's right.
Right. So you're going to lose
Yeah.
second harmonic faster
Faster.
than fluorescence.
That's correct. That's correct, yes. That's absolutely correct.
So you said that the second harmonic generation from the NADH.
No, second harmonic generation is exclusively from collagen 1 in this case. The two-photon fluorescence is from NADH.
Right.
Yeah.
Just looking at that picture, well, why don't you see second harmonic generation from melanin, or is there no contribution to that?
Melanin has no second harmonic generation. Only two-photon fluorescence from melanin. The melanin fluorescence is not picked up here because it actually occurs at longer wavelengths more efficiently. So this is predominantly an NADH picture here. Yeah, from the two-photon fluorescence. The collagen is, the blue is exclusively collagen 1.
Or collagen 4, right? This is based on membrane, right? So it should be collagen.
Yeah, but
Not really, or is it two?
this is really dermal collagen.
That's dermal
Yeah.
collagen.
Okay, so we talked about two-photon fluorescence and second harmonic generation. There's also an important class of nonlinear optical techniques that actually probes things like this. The spectroscopy, the vibrational spectroscopy of molecules. And you probably have seen vibrational spectra before. These lines, these energies correspond to vibrations of the molecule. Okay? Vibrations of particular chemical bonds. Every molecule has bonds, and they have particular energies at which they have a vibrational resonance. And you can shake those. I will not go through this. But if you're interested, I can explain it to you. But this process here is a very good way to probe those vibrational energies. Okay? So this is a vibrational energy. It's a very low energy, and it's nowhere close to the energies that we put in typically in a microscope. You see, it's completely off-resonant. However, sometimes this happens. You put in an off-resonant energy, you again go to these virtual states of the molecule, and the molecule is able to fall back into a vibrational eigenstate. Okay? It can do that if it emits this photon. And so you can intercept this photon, and then the difference between the photon that comes out and the photon that comes in tells you the energy of the vibrational state. That's called Raman spectroscopy. Raman spectroscopy is a very popular tool among chemists. This is what they use to analyze their molecules. They can see what kind of chemical bonds does this molecule have. So this is a beautiful way. You can use visible light to probe kind of low energy, infrared energy vibrational transitions. Very nice. There's a big problem, and that is that this process is extremely inefficient. And you can buy a Raman microscope from several manufacturers, beautiful images really, but it takes a long time to collect those images, hours and hours. Okay? And that's because the photon flux of this red arrow here are very low. And so that's not interesting for tissue imaging. Tissue imaging, we need things fast. Real time, ideally. Video rate. So here is another way of doing the same thing, much more complex, but if you look at the first section here, it's the same. What we do here is we come in with this first pulse, then we have a second beam that's not just emitted by the molecule, but just applied by us. So 1, 2, these two guys actively drive this transition, and then this photon converts that information into this green photon that we can intercept. This is called a nonlinear Raman process, which is much more complicated than linear Raman. But the only thing you have to remember is this photon that we detect comes out at a much higher rate than this spontaneously emitted photon by the molecule. So we have taken the molecule basically for a ride here. Okay? So the molecule is able to give us this information, but we force it to do so faster by applying some extra light to it. We drive the system more actively, we get rid of the spontaneity of the molecule, and we decide when a molecule gives this photon, and that this photon is emitted in coherence with the photons emitted by its peers. This is the microscope that we use to do that with. This is a regular microscope, a laser scanning microscope. Same microscope we use to do confocal, to do two-photon fluorescence or second harmonic generation, can also be used to do this nonlinear Raman. In fact, you can do all these things at the same time. Okay? Here are the ultra-fast lasers, some limited optics. All of the magic happens in this laser scanning microscope. Now, the interesting thing is that this coherent Raman technique is truly coherent. What does that mean? So here, this picture we've already seen. This is the focal volume. We know the signal can only be generated here in these brightly colored regions. Okay? That's where the intensity is the highest. However, I also showed you the phase. The phase thus far has not been so important, but for these coherent techniques, which also includes, by the way, second harmonic generation, this phase is going to be important. What does that mean? That means that the molecules are driven with a slightly different phase here, this region, than there. I think the color is different. They're driven with a different phase. Okay? So we have to take all of these effects into consideration. And this is going to be very relevant for kind of understanding the emission of these nonlinear coherent signals in tissues where we actually disturb both the amplitude and the phase. We cannot just understand the emission anymore with just an intensity picture in mind. We have to kind of decompose it into amplitude and phase and look at both effects. So let me give you kind of an illustration of that. Here's my focal volume. Okay? So here, this is the area where molecules can be driven. And let's say I have 2 points, 2 molecules, A and B. Okay? And I'm driving molecule A and B with my laser field. So they're driven with a certain phase. They start to emit light, and let's say the light is traveling in this direction. It's going here into my far field. This is my detector here, far away from the focal field, right there. And molecule B is also emitting a photon. Okay? These A and B are driven by the same laser field. They have the same phase in this plane. And so the length of this arrow and this arrow determines how much of the signal I am able to collect at this location, because there's coherence between A and B. Okay? That's the whole idea of coherent microscopy. So every point here contributes to rays all over this detection surface. And if I want to have any point here on the detection surface, and I'd like to see what the intensity is, I have to add up all the waves from each point, from each emitting point in my detection point right here. Okay? And then I have to add up all those waves, interfere them, and determine what the overall intensity is. So Here's this is a calculation. This is exactly what we've done. This is basically my focal volume. Lots of molecules here. They all emit waves, but the waves are in phase. So if I want to know the detection and what the intensity is on this plane, what I have to do is for each point in this plane, add up all the waves that arrive there, interfere them, and determine the intensity. That's basically shown here. So here you see as a function of angle. This is angle 0, which means this point. This is moving away from angle 0, which means I'm going on this area right, going on this curve right there. So away from the forward propagating direction, this direction, away from it, I get less and less, 0 or 90 degrees. If I put my detector here, I don't see anything. Okay? Put my detector here, I see a lot. That's what it means. So this coherent emission is very different from fluorescence. In fluorescence, it's almost isotropic. Wherever you put your detector, you see something. If you put it at 90 degrees, in fact, you still see something. In this coherent microscopy, you do not. Okay? The emission is very well defined because it constructively interferes predominantly in this direction and not away from it. Now, this is interesting, very quick. You see here, one little tiny dipole, one little object, one molecule. If I drive that molecule and it emits, you see it emits in all these directions. This is the shape of a Hertzian dipole. Okay? So it emits a lot in this direction, a lot in this backward direction, and to the sides, but nothing in this direction. This is the direction in which I shake the dipole at. If I actually make a plane of several molecules, I see the same kind of effect. It becomes a little bit more confined. It goes up and down. Same for a full plane, up and down. So emission goes up and emission goes down. Okay? But if I fill my entire focal volume with molecules, a lot of molecules contribute. If I then look in which directions it emits, it only emits in the forward direction. Because only in the forward direction those waves are adding up in phase. In all other directions they are destructively interfering. Okay? If I only have half my volume occupied with molecules that emit, let's say the upper half, then in this direction there's still a lot of constructive interference, as you can see. There's a little bit left in the backward direction. Look at that, little tiny guy. Okay? A little bit of light is left that travels back. So you see, if I occupy my molecules throughout the entire volume, only forward light is surviving. But if I kind of have less than that, I also see some light surviving in other directions, like the backward direction. So this is a story completely different from fluorescence. Complicates the story quite a bit. In fluorescence, the light is isotropically distributed and is directly proportional to the concentration of the molecules. Here, very different. Here I have to look at the wave interference. Okay? And it leads to very interesting emission profiles. And you can understand if you have scattering coming into the mix here, it becomes even more complex. Because this depends on the phase distribution of the focal volume as well. Okay, here's a kind of a funny effect. Here you see an object that has a certain diameter d, okay? And the bigger this object gets, you see that the emission in the forward and the backward direction is going to change. This is really interesting. You won't see this in fluorescence. Always remains the same. So in the forward direction, you get more and more and more and more and more and more as the object grows. That's because it's always constructively interfering in the forward direction. But then if the object grows, in the backward direction it gets some little bit more, then it goes down, up, and starts to oscillate and goes down when the object becomes very, very, very large. Because the larger the object, the more destructive interference in the backward direction. So you see the forward and the backward direction, depending on where you put your detector, you see a completely different image. Okay? Here, this is the forward image. This is the same cell seen in the backward direction. It's the same cell, it's the same optical process. But due to propagation effects, coherent propagation effects, you see a completely different kind of contrast, right? So these coherent effects are very important to take into the picture in order to explain the images that we see. This is not what you would see in fluorescence. In fluorescence, you would see two identical pictures. Okay, now, fortunately for us, scattering can actually work in our favor a little bit on this level. So, let's see, we do this coherent experiment, we do this CARS process, let's say. I generate light, okay, and now in the tissue, my molecules kind of are everywhere, they fill up the focal volume. Let's say you have a big chunk of a big fat cell that contributes to the signal, so the entire volume contributes, and most of the light will be going forward. You don't see a lot of backward light. The objects are large and not small in the tissue, so a lot of light will be going forward. That forward going light we don't see because our detector sits on the epi side of things. Right? If you have a thick tissue, you cannot put your detector on the other side of the animal. The light doesn't come out. You want to detect on the backward side, the scattering side. So your detector sits here. So what is the light you intercept? It is actually the light that's generated forward. That's the direction in which it constructively interferes. But then, due to scattering, part of that forward propagating light is back directed into the epi direction, the backward direction, and that's the light you intercept. So, if it wasn't for scattering, you wouldn't see anything. Okay? Scattering in this case actually helps us out. We need it to do this coherent type of spectroscopy, coherent type of microscopy. Here's an example. This is a mouse tissue is live. This is an image at video rate. This is Cars microscopy. You see some nice structure. This is sebaceous glands. Let me show you a better picture. This is a 3D rendering of that. You see the stroboscorneum of the mouse. You see those structures, the sebaceous glands. It's very bright because we tune to the lipid stretching vibrations of the CH modes. So we see lipids here, and the sebaceous glands have lots of lipids. So these structures, which are about 60 microns in, give you a lot of signal and can be intercepted at video rate because the light is traveling into the tissue but is then scattered back out, and that's what we detect. Again, if it wasn't for this effect, there's no way we could have done video rate imaging in a living animal. Another example, this is actually blown up at slightly higher resolution of the sebaceous gland. In the tissue, you see, this is one cell, this whole thing is one cell. Lots of blobs in there. Those blobs are individual lipid droplets. That's what this cell is doing. It's making this sebum, which is lipid, synthesizes it and squeezes it onto the hair shaft, which is the hair right here, the hair. And so this is the oily substance made by this cell that is lubricating your hair. But you can see this is a label-free image in the tissue, taken at a very high rate, and you can see a lot of detail. This is where the power of this type of microscopy lies. And you can combine, of course, these techniques that we have talked about so far with one another. So this blue here is, again, collagen second harmonic generation. This green is the emission, fluorescence emission from elastin. And then in red, I see the CAR signal from fat areas. These are adipocytes. This is a kidney tissue. This basically is a blood vessel. Collagen, elastin, and fat that surrounds the blood vessel. And this is all label-free, no labels, and it takes 1 second to take an image like this. All taken at the same time. So clearly, these techniques have a lot of potential to be used in live tissues. You can get this contrast without treating a tissue, and you can get it fast. I will not talk about this, Wasson. Just skip this, okay? So because it's just a little extra thing. I'm just going to the final slide. That's this. So we have these beautiful techniques, these focus-based nonlinear optical microscopy techniques that have a clear advantage over confocal microscopy techniques. Confocal microscopy, which in the first place uses fluorophores, which we often don't use in NLO microscopy, and confocal microscopy that is much more sensitive to scattering than nonlinear optical microscopy, primarily because of the longer wavelengths we use in NLO and because of the wide area detector that we can use in nonlinear optical microscopy. So nonlinear optical microscopy has become the standard kind of to do tissue imaging. But its performance is limited, and it's limited primarily by scattering in a tissue. Scattering does attenuate and distorts the excitation volume, and that is the main limiting factor. It affects the penetration depth of a microscope. And that is just really, really unfortunate, because we would like to go much deeper than we can. A lot of diseases happen at a depth beyond 500 microns. Okay? And we cannot get there. We cannot get down to 500 microns. Even if we play all the tricks that we know of, that is just out of reach. And that is very unfortunate, because the contrast that we have is beautiful, it's label-free, it's very fast, but scattering perturbs the focus, and therefore we cannot generate enough photons. We can't get them out, right? So scattering is really the limiting factor in nonlinear optical microscopy. So, you know, it's worthwhile thinking about this. If you can solve this problem or even make it remotely better, I mean, you actually gain a lot, right? If you can get down to 500 microns, you actually will have a lot of new friends, I can tell you that. Okay. So, and it starts from understanding where all of this stuff comes from. Why does it scatter sometimes a lot, sometimes it doesn't? What really are the critical parameters that perturb this resolution and signal collection? So we have a general idea. Intuitively, we understand what's going on. But really, what really happens, we don't really know so well. So hopefully from a better understanding, we can think about ways to reduce it, tricks to reduce it. Can the effects of scattering be counteracted? Can they be preempted? Or can they just be dealt with? Are there like detection schemes that are smarter than we currently have that can actually kind of cancel out scattering? Who knows? These are things to think about. And of course, the overall goal is to do that and to go deeper. Okay? If you can get down to 500 microns, suddenly you can actually say something very significant about skin cancers, for instance, in exposed skin or even in the mouth, where oral cancer is a significant disease and is manifesting itself on the order of 500 microns, half a millimeter below the surface. So getting to these areas is really, really important, and so hopefully you guys can start thinking about that.